Thanks very much for having me here. Yeah, I was already talking to some students here. I guess it was a student, and he told me, hey, I was expecting a coding talk. And yeah, we do a lot of channel coding, error correcting coding, but we also do wireless measurements. We do signal processing for wireless systems, also for optical systems. And I thought, well, maybe there aren't too many coding experts here, so let's talk about wireless. Wireless is much more easy to understand. It's much more accessible, right? And I'm not talking about RIS or RIRS. I'm keeping it simple. Okay, communication sensing only works if you have a great team, and I do have a great team. Some of you may know, for example, Florian and Philip, Mark, and Moritz, Ephraim, and Daniel. They are all about to graduate. Some of them are about to graduate, but I try to keep them here as long as possible at the Institute, of course. All right, so let's get into the topic. I was giving a keynote presentation 2017 at, was it Munich? I can't remember, or Berlin, on the workshop on smart antennas. And that was part of my slides. And I realized, hey, this was before AI, machine learning, deep learning, communications, pretty much. And it was also before communication sensing, to me. Like communication and sensing got into my research field around 2020, and we had the first project on this. And machine learning, deep learning came into the game about 2017 to 2018. So that was like my last presentation that had no ML, no machine learning, and no communication sensing. From now on, we have to work with that. So. And yeah, you see, all sounds a bit outdated. Vectoring for wired MIMO and all this stuff. Hybrid MIMO was big in those days. Massive MIMO, okay, 2010 already. And it all started, of course, with BLAST and for skinny Teletype 1995. Multiple antennas in communications. Well, again, I hope to have something for everybody here. It's more like an overview presentation. We have open loop and closed loop. Open loop is in widespread use in many communication standards today because it doesn't require feedback and it nicely scales up the capacity of your channel as you increase the number of transmit and receive antennas, right? And that's illustrated in the top right figure. Now going to closed loop, we do massive MIMO or multi-user MIMO. We use a lot of antennas at the base station, many antennas, more than 64, 256, whatever. And we use them for spatial multiplexing uses in a cell, in a spatial area, right? So that's much more difficult because the channel is much more dynamic. People are moving around and they have to report back their channel to the base station such that pre-coding can be done appropriately. And yeah, that is not really in widespread use, by the way. One reason for that is that we have FDD, like uplink, downlink are separated by a few hundred megahertz, and you cannot use reciprocity of the channel to infer on the downlink channel for pre-coding by using what you see on the uplink. That may change in future standards that you use TDD, like use uplink, downlink in a time division, time duplex division fashion to don't have the overhead of feeding back the channel. So that's multiple antennas in communications. Multiple antennas in sensing. Very old story, 1940s. Radar, phased arrays, chirp impulses. People use synthetic aperture radars today to have a large aperture by having transmitter receiver in our terminology moving around, and that way creating a large aperture that you don't have to have implemented in parallel in the antenna space. And then 2020, something like ICAS, integrated communication sensing, or JCAS, joint source and channel coding. No, joint sensing and communication. I'm a channel coding guy, it seems. Yeah, made its appearance, and it's a strong contender, of course, for 6G. And all the companies, all the wireless mobile equipment companies, be it Ericsson, Nokia, Huawei, you name it, they are working intensively on this topic. And also we are doing stuff there, as you will see. So I will talk about the sensing communications today. Different terminology. Monostatic just means from one position. Multistatic, meaning transmitter receiver are at different positions. Monostatic is much more demanding with respect to isolation, right? You have a lot of scattering and false alarms, if you will, false detects if you do monostatic. Multistatic is simple in a way, but also more difficult to synchronize. Many different aspects. So a lot of new signal processing challenges that came into play of the communication engineers, right? I mean, we are used to protect information, channel coding, stuff like this, 16QM, whatever, you name it. Receiver processing, now we also had to care about calibration, much more about synchronization. And that's, for me, an important aspect when we teach this in master's courses, parallelogram, where you do FFTs over antenna space for the angle and over frequency space if you use OFDM for distance, time of arrival, and stuff like this. So that has now become the rule of the game and no longer just a bit array chart or something like this, right? All right, and how did we get into this topic? So we used to have a channel sounder that we applied for computing channel capacities of different environments. And we beefed it up in order to provide time-calibrated measurements, phase-synchronized measurements, to use that data for the sensing task. So now we can not only do theoretical work, but we can also do measurements and see how our algorithms work in practice. Like there's stuff like not that old crap and scrap for clutter removal that we contributed, or there is all these super resolution techniques, music, and so on and so forth that you can apply to these type of data that we will measure. So not only based on theoretical considerations. Okay. Outline. And I'm trying to focus on 1, 2, and maybe 3, and 4 and 5 are optional. You have the slides, so you can feel free to contact us, feel free to browse through, and maybe you find some interesting stuff that you where you want to get feedback from us. DICASUS, that's how we got into this topic. We do measurements. How do we do measurements? Well, not only the conventional measurements that we used to do, but we also extended it to a distributed massive MIMO channel sounder. Now, left side, you see one base station antenna. Does it have a laser? Oh, let's say that's a base station antenna, that's the user. You do pre-coding, beamforming, done. In a distributed setup, you have different arrays in whatever different topology, and you form beams by synchronizing these guys, right? So it's still one base station, it's still considered one antenna. It's not like what people would call comp or so, like through the network. It's still one base station site, and you coordinate this and form beams. So that's what we call distributed massive MIMO. For this, these guys need to be tightly synchronized. So when you do measurements, the challenge is to synchronize these guys. All right. Now, what did people do in the past? Well, different measurement vehicles. Also, we had this measurement vehicle 1.0, 2019. Now we replaced this a few years later. So that was very basic. And it actually took all these multi-antenna signals and on one frequency and shifted it to different frequencies like a frequency multiplex signal on the receive side, and then a digital oscilloscope with a large bandwidth digitized to one A to D. Right? So that was very, very synchronous as you can be. The problem is that this A to D in here was the bottleneck, so not a very high resolution. So we killed this, and this you cannot distribute this, right? So you only have one receive antenna site, right? So we broke this up and use now different DSP chains for each antenna and synchronize them over the air. So there's one beacon transmitter that synchronizes all the receivers, and the receivers could be distributed anyhow, but all need to see the beacon signal. Okay, that's the thing. And we built 2x4, like 8 antenna elements. They could be then totally separate. Even one element in principle could be separate. Each element has its own RF and DSP A to D chain. And they are separately dumped on USB drives and then later offline combined. So this is not real time, this is offline processing. A couple of specs up to 64 antennas. Each antenna can be dual polarized. All right. So that's diacasis. You can do all sorts of measurements. And that's a cool demo I want to show. Let's go to the demo. Maybe it even works if I press this button. Yeah. Oh, it works. Okay. So what I want to show is that we have a space 4x4 or 5x5 meters. This is a robot that's now moving around. And here also is the antenna area, 32 antennas. Now this guy now starts moving. Start moving. You can do it. Yes. So now this is running around. It's a robot that can be programmed to do whatever. And the receiver is here, sees these 50 megahertz, 1024 subcarriers, 50 megahertz spectra, phase and magnitude. And you see how this changes like crazy. But the challenging task was that when you return to the to this side, so this robot has a transmitter antenna, this is the transmitter, then the channel of 5 minutes ago coincides with the channel right now. It's very difficult because a communication system doesn't need to do this. A communication system only needs to be coherent, phase coherent, for the time of a packet, like Wi-Fi or so. But to do measurements over hours, this is very difficult and requires a lot of calibration. And of course, as soon as someone moves around in the room, it also changes the channel, but that's okay. That's what we want to measure, maybe. Right? But we don't want to get any artifacts of the system. So the system was very hard to calibrate the system, but it works. It works. This is 1.25 gigahertz, but it also works in 3.4 gigahertz and of course 2.5. All right, let's go back to the slides. Yeah. Okay, so we have a website, a lot of data sets. We have, like each data point has 1024 complex CSI values for the 1024 subcarriers. And 64 of them because we have 64 antennas. So it's a lot of data that we can accumulate, and also it's position tagged. So you have a position where this measurement was taken. We use a tachymeter, robot tachymeter. Where is this thing? That's a tachymeter. Leica or other companies or size that track this and give a position. All right. So measurements, we have a production hall for the university where we can distribute. That's a distributed setup. Where's the robot? There's the robot. So that's the transmitter. And we have 64 antennas distributed and do measurements, and that's all perfectly calibrated. Then we can do whatever we want. All right. Channel charting. That's one application of this data. What is channel charting? Channel charting is communication sensing. Actually, it's sensing. It's sensing, but using communication hardware. And it is trying to infer on the position of a user, say here's a user, by radio measurements at cell sites. And it's not classic. It's not a classic time of arrival, angle of arrival, whatever. It is based on, it's a relative positioning method that's like self-supervised, if you will. It works with similarities in the CSI values. So two measurement points are supposed to be close to one another if the CSI values in some metric are close, and if the measurement time is close. And this way we can come up with a chart called the channel chart that has a shape which resembles the actual track or trajectory that was driven, but scaled, distorted, doesn't matter. It's just a relative position. It only provides a relative position. So this algorithm can tell you, these 2 points are close to one another in a CSI sense. And of course, the cool thing about this works for non-line of sight environments. And your classic positioning things, triangulation, whatever, they don't work in non-line of sight. This works in non-line of sight. So you could call a channel chart also like a neighborhood map or so. And it was invented by Christoph Studer from Zurich. And I have a timeline later. So that's one big thing that we do a lot of channel charting research. Some more details on how channel charting works. Channel charting essentially takes you have a point with 1024 times 64 complex values, and it projects it onto XY. So the output is XY. And of course, this can be done by a neural network, and it can be trained. And then you get relative XY coordinates, not absolute. Now you can trick the system by providing ground truth. Hey, you know what? I have a beacon. I know that this point actually was here, XY, and here. And then you can take this channel chart and you can unskew or deskew it, and it becomes the actual position. That's cool. All right. Oh, yeah. Dissimilarity metric. So that's now in the language of learning, training of networks, and fused with, there's a time and a CSI distance, and that's used to train this multi-dimensional projection function. All right, some favorable neural network structures that work well. And that's what I wanted to show, the timeline of channel charting. So channel charting was invented 2018. Hey, that was just right after 2017 when deep learning came into play for wireless. And just before 2020, communication sensing came into play. What a coincidence. And then it had all different stages, neural networks. Actually, the first one was not using any neural networks. Then neural networks, different structures, and so on. Yeah, and data, and of course, synthesized data first. Passive, so that's pretty new. You can also do channel charting using passive objects, like a passive target. This robot that was driving around, that emulated someone walking around with a cell phone. So it was actively transmitting, and our base stations or distributed base station received the signal. And this way, it was able to record CSI data and to infer on the position, even in non-line of sight positions, right? In non-line of sight situations. Now, this passive channel charting works more like a classic radar, multi-static radar. You have, we did this in Wi-Fi, we do this in Wi-Fi. So you have Wi-Fi transmitters here, and you have receivers here. So that's what's called a multi-static environment. And this way you can also train to to locate people, say, in a room, right? All right. And that's actually what we do with what's called asparagus. Show you in the next slide. One of the next slides. Okay. That is like, this is this area, this sock-like area, like that looks like a sock. That's ground truth for training. Doesn't need this, but it's easier to evaluate the precision of the prediction. And that's then what comes out if you use this channel charting. All right. Okay. Passive stuff I talked about, pretty new. If you're interested in that, let us know. There are only like 5 teams in the world working on this stuff. It's like a family come together when we meet at Asiloma or so. It's like Maxime Guyon in Lyon. It's Christoph Studer and group in Zurich. And 2 other groups, one company group, and yeah, always fun. Good. And actually, it's attractive for application because it doesn't require ground truth. It works by by just comparing, and you get this relative map. Differential ray tracing. Not sure if I want to. Maybe a short note on differential ray tracing, because it's also a new method that's useful for sensing, and we can use our data for. What is it? Well, you can, again, that's a hallway. That's our institute. It looks pretty much like your institute, Eduard. Also, these hallways all the time. We have 2 receivers and a mobile transmitter that runs around this whole thing, line of sight, non-line of sight, whatever. And we collect this data set. And differential ray tracing, that's shown for a different situation. Differential ray tracing is a ray tracer. Of course, you have to have the full model in the ray tracer that is differentiable. That means, plenty of time. That means differentiable means that you can run back propagation on this ray tracer to find the best matching material properties to coincide with measurements. Okay, so think of this: you have a hallway in the ray tracer, perfectly modeled. The surfaces are typically given as, you know, how they reflect, how they absorb, how they polarize, and things like this. And you have assumptions. Well, maybe a metal wall is like this, a floor is like this, a ceiling is like this. And then you start the ray tracer. It spits out a result for a certain data point here, right? Assuming different receive antennas, you have the same receive antennas as in real time, in reality. And then you do the same thing in reality. Of course, now you have everything is real, right? And the material properties are slightly different as the assumption. And then you let this run through you come up with a loss function. And then you train the material properties such that they coincide, and then you figure out, hey, the floor has this type, the ceiling has this type, the walls have this type. And then it's like you can do like some tomography on the environment based on this. And it's also pretty cool. The results are shown here. So that's our hallway simplified. And then that's the result in terms of, there are different parameters. That's like specific reflection coefficient. You have to go through this paper to understand what this is. And it's non-trivial, of course. But the cool thing was that the material properties, they kind of converge to 3 different ones, like one representing the floor, the ceiling, and the walls. And that is an indication that the results are plausible, right? Because, I mean, some of the material properties probably are not really the material properties, but the different physical modeling of the environment, because it doesn't perfectly, like this plant is not in there, so then it maybe changed the material properties back there because the plant was not in the ray tracer, things like this. But it's a different way of sensing the environment, right? Of course, you need a very good physical model in your ray tracer, but then with the measurements, you can see what happens and in terms of material properties. Okay, quickly running through this. We have this in real time. So this Florian Euchner, and he built an array which can be you can connect those, so you can build 64 antennas or whatever with Wi-Fi chips. So he found ways of synchronizing the Wi-Fi chips, and then you have a phased array, and you can do all of this stuff in real time. And well, he also played some gimmicks, like that's a circularly polarized antenna. And you can visualize this as like a circle in a software. And if you put what is that? An oven grid, whatever, then you see nicely how this polarized in one direction. Well, probably too much to go into this. And you can buy this, right? You can buy Asparagus. I have no stocks in this. I don't benefit from this at all. But he's still a PhD student. But there's a lot of interest from academia and also from police. The Dutch police uses this, and other companies to do all sorts of things. So if you need this for projects, whatever, it's nicely documented. Has a lot of scripts, Python scripts. You can do your own measurements, right? And do whatever you want with those measurements. All right. I think let's skip that. It's in the slides. Maybe one last, no, summary. Thank you. Any questions?
Sounds a very interesting talk. Any questions?
Thank you very much for your interesting talk. I have one question for the distributed MIMO. So you said that like this time synchronization is very important. And I was wondering about the spatial synchronization. So if the antennas sway on a wavelength scale, for example, this would distort the measurement completely, I think. And
say it again.
If the antennas sway in wind or something.
Oh, yes. Oh, they have to be fixed, of course.
I'm also interested in, for example, in the channel charts, how sensitive this is to antenna misplacement or noise in the placement of the antenna.
Okay. Yeah, thank you. Very good question. The first thing is, if you can place the antennas in any way. You have seen that the antennas are built, for example, in blocks of 2x4 in a phased array structure. Don't have to be. They could be completely randomly, right? Only if you want to work with specific algorithms on the data, where you need to know, oh, it's lambda/4, whatever, lambda/2, whatever, then you need the specific spacing. How sensitive is it? Well, if people walk around, it doesn't matter much. The antenna, we haven't really had the antenna wobbling around. The antennas were always fixed. Yeah. Well, they tend to be fixed, right? But a good question. Yeah. I answered the question, kind of.
Thank you for your nice talk. In addition, I would like to ask how costly is the synchronization task? So I think you have to redo this a lot, or is it like you can synchronize it once and it stays like this for hours, or
okay?
What does it look like?
So we have the two systems. Like one, this Dicasus is more like an academic offline channel sounder that has higher bandwidth and everything. It's better from an academic perspective, but requires this beacon transmitter that all the other antennas have to see. So which is nice in the sense that there needs to be no wire or even now for Asparagus, this other thing, which is based on Wi-Fi chips, we have the beacon transmitter on the PCB board. So you have, like, if it's not really distributed in the sense that if you want to do distributed measurements, you would have to have a wire from one PCB board to another. It has pros and cons. Yeah, what's the question? From a timing perspective, doesn't cost anything. No. Okay. Oh, one more question. Yep.
On your channel sounder, you said you used the new one, the DACUS or whatever it's called. Yeah, the new one, the one. Well, the one, yeah, DACUS. But if you have something newer, maybe you can talk about that. All right, yeah. You mentioned you use the software-defined radio for it. I'm just curious as to which devices you used, and also how do you deal with the volume of data that those things produce? You said you do offline processing. I've encountered that. I had to use basically a supercomputer to process data from 4 E2's X310s for my experiments. Do you use any processing on the FPGA or the radio itself? What kind of just mechanics of this? I'm curious to know how you solve these problems.
Very good question. For DACUS, it's really raw IQ data. And it's 64 or even 128 times like a USB drive of say 512 gigabytes. And then offline, we have to compute text 2 weeks or so to then spit out the data that we put online. That's for the Aspargus, we use the Wi-Fi receiver. So FFT, everything is done. We can directly tap into the CSI values on the subcarriers.
I see.
So that's much easier. The 50 times less data.
What radios did you use for DACUS? Do you remember?
For DACUS, that's analog devices. It's a Pluto SDR.
So I'm surprised you were able to accomplish so much with Plutos. Your group must be quite good at actually extracting everything that they can do. Cool, thanks.
We definitely are. Thank you. Yeah, the data is online. So if you want, we have a website with like one data set is maybe 100 gigabytes of data, but already processed. So this is the CSI data you want. You don't have to do acquisition also. Okay, thank you.
Thank you for your interesting talk.